rotary hearth furnace, where basically iron ore is reduced either to the DRI or nuggets depending on the operating parameter, and then that reduced uh, DRI or nuggets are further melted in the electric arc furnace and finally refined to produce the crude steel. Okay, and in this process, basically we are utilizing iron ore fines and non-coking fines. They are basically mixed earlier before charging in the rotary hearth furnace in the form of composite pellets. Okay. And if the RCA product, depending on the operating parameter, as I told you that they are either nugget or DRI. Nuggets are basically 100% metallized iron, and if you look into the composition of the nuggets, they are similar to that of the pig iron. And in nuggets, basically, gangs of the iron ore is separated out. Whereas in case of DRI, the metallization percentage varies between 87 to 92%. But the main problem with DRI is that the gang associated with the coal as well as ore remains in the DRI. Whereas in case of nugget, they are separated out. But if the RHA product is nugget, in that case, the steel making process is known as ITMK3 electric arc furnace steel making process. Whereas if the RHA product is DRI, in that case, the steel making process is known as fast melt electric arc furnace steel making process. Now, a combination of rotary hearth furnace with electric arc furnace may provide unique opportunity to lower energy consumption through scrap recirculation as well as the lower CO2 emission because of the dual fuel use. Here, the lower energy consumption because if you go for the conventional blast furnace basic oxygen furnace route in BOF, the scrap charging is limited to mostly 15 to 20% only. But in case of since in RHF, there is a possibility to charge higher amount of scrap since we are melting in electric arc furnace. Similarly, since as I told you that RHF are based on a dual fuel use, therefore there is a possibility of low CO2 emissions. And it is claimed that RHF EF process requires lower carbon and also produces lesser CO2 emissions than that of the conventional blast furnace basic oxygen furnace processes. And it is expected that RHF EF process operate at higher exergy efficiencies. We will discuss later what does we mean by the higher exergy efficiency because of the lower CO2 emission per ton of crude steel based on the dual fuel use in rotary arc furnace and possibility of higher scrap input in the electric arc furnace unit. Therefore, there is a scope exists to analyze the sustainability of the rotary arc furnace electric arc furnace steel making system by study the exergy flow and CO2 emissions from the RHPF system combined together. Now, before going into the exergy analysis of RHF-EF system, first we discuss about the concept of exergy. That means what does we mean by exergy? Now, as all of you know that energy is basically ability to do some work, whereas exergy is the useful work potential. So we can say that energy has two components. One is exergy and second one is energy. Exergy is basically useful work potential, whereas the energy is the unavailable energy. And this can be understood by one simple example. Suppose we take 1 kilojoule of energy in two forms. One in the form of electricity and second one in the form of energy in the form of hot water at 70 degrees centigrade. And if you try to convert these two energy into some useful work, in that case, electricity can be completely converted into some useful work. So you can say that in case of electricity, energy is equal to exergy. But in case of hot water at 70 degrees centigrade, we cannot convert all the energy into useful work. At max we can convert only 13% of the total energy into the useful work, and remaining 87% are the unavailable energy. That's the main difference between energy and exergy. So the major characteristics of exergy is that it can be destroyed, but energy cannot be. And so we can say that the exergy is the useful portion of energy. Now coming to the exergy calculation, basically exergy has two components. One is the chemical exergy and second one is the physical exergy. And chemical exergy basically defines as the maximum amount of energy that can be recovered if the system is brought chemically equilibrium with the reference system or dead state, we can say. Whereas physical exergy has further four subcomponents. One is the thermal exergy, mechanical exergy, kinetic exergy, and potential exergy. And thermal exergy basically due to the temperature difference between the system and environment, and mechanical exergy basically due to the pressure difference between the system and environment. Whereas kinetic exergy due to the flow of steam, and potential exergy basically dependent on the position of the steam from some certain reference level or datum level. Okay, and in case of high temperature pyrometallurgical operations like blast furnace or steel making furnaces like BOF or electric arc furnace, the values of thermal exergy is quite high compared to that of the mechanical exergy, kinetic exergy, and potential exergy. So in the present study, those values are neglected. Okay, since the these values are either close to zero or negligible compared to that of the thermal exergy. So in the present study, whatever physical exergy represents only the thermal exergy part. Now coming to the how we can calculate the chemical exergy of any component or element. Okay, uh, since these value, if you go for the uh, calculation of exergy of any compounds, these are basically standard values. You can take this value from some standard references also, but for your understanding purpose, I am just giving you how we can calculate, how is these values can be calculated. So as I told you that when any system or the compound is in dead state, its exergy value is zero. Okay. So and for most of the cases, the reference stage is taken as their average composition in the earth crust. Like if you look into the average composition of the Fe2O3 in the earth crust, it's around 1.3 into 10 to the power minus 3 only. Okay. And that is the datum or dead state of the Fe2O3, and where the exergy value is 0 kilojoule per mole. Okay. But suppose you want to extract Fe2O3 from the earth crust, that means that in that case you have to supply around 16.5 kilojoule per mole of energy. Or we can say that when you convert the Fe2O pure Fe2O3 bring back into the dead state at the average composition level of the earth crust, in that case you can maximum theoretically recoverable energy 16.5 kilojoule of per mole of energy. That is so this value is basically chemical exergy of Fe2O3. And for chemical exergy of Fe, you can, once you know the chemical exergy of Fe2O3 as well as the chemical exergy of O2, since Fe2O3 is composed of Fe plus O2. So you can easily calculate the chemical exergy of Fe, and this value is a standard value like 376.4 kilojoule per mole. That is the chemical exergy of Fe. Similarly, you can calculate the chemical exergy of all the elements or compounds that are present. Okay. So this way, and this value are very much standard value, and you can take this value from any references. And as I told you that the reference state may be your gaseous atmosphere or in the earth crust level or sea water also, depending on their composition. Now coming to the exergy calculation of the various streams that are basically utilized in iron making and steel making, like iron ore or gaseous stream or hot metal slag. For that, for calculating the chemical exergy, basically equation 1 can be utilized for computing the chemical exergy of any stream. Either it can be hot metal or slag stream or the gaseous system also, where the first BEL basically represents the summation of elemental exergy of all the elements present in the stream, and the second term basically represents here the free energy of formation of all the compounds or phases that are present in the stream. And basically third term delta G mix basically represents here the free energy of mixing of all the compounds or phases present in that stream. Okay, for the condensed phases like solid or liquids, the delta G mix value is very less compared to first two term. That's why they are neglected. But in case of gaseous stream, you cannot neglect the delta G mix. For calculating the delta G mix, we can utilize this equation. Delta G mix is nothing but the summation of delta H mix minus T naught delta S mix. Okay. And as I told you that earlier, that the physical exergy basically represents here the thermal exergy part also. And this can be computed by equation 2 as shown here, where the first one delta H basically represents the total enthalpy content of the stream. Whereas the second term basically represents here the irreversibility of the stream, or we can say that the entropy generation. And summation of physical exergy and chemical exergy, that will give you the total exergy of any material stream. And the components of equation 1 and 2, okay, they can be easily nowadays calculated by using some thermodynamic software like thermocal or FACSES. For the present study, I have utilized FACSES 6.4 for compute these values. And this figure here shows here what I have explained here. Like initially we have to estimate the elemental exergy of all the elements present in the stream, and summation of there gives you the elemental exergy. And then if you sum this with the free energy formation of all the compounds of phases, that will basically give you the chemical exergy. In this figure, I have not shown the delta G mix part, but if you deal with the gaseous system, you have to consider that part also. And and similarly, we can easily calculate the physical exergy, and their summation give you the total exergy part. Now the question arises why we need the exergy analysis in any industrial process, not only for the iron making and steel making, but any industrial process. As all of we know that in most of the industries, basically energy analysis is conducted, but that is basically simpler in nature, and it basically deals with the only quantity of energy, whereas exergy analysis deals with the quality of energy. And energy analysis is based on the laws of conversion of energy. That means energy cannot be destroyed; it can only be transformed from one form to another form. So energy analysis neither provide any information about the degradation of energy during the process, since during the process energy quality may degrade, or nor quantify the usefulness or quality of the various energy stream associated with the stream. Okay. Whereas exergy analysis helps in finding the following, like it can be utilized to determine the type, location, and magnitude of energy losses in the system, and further it can be utilized to find the measures so that we can enhance the energy efficiency of the system by reducing the energy losses. Now, energy exergy analysis provide also the true measure of the how system is deviates from the ideality. Okay, that means since in any irreversible system, the system is deviates from the ideality, and then that can only be measured by the exergy analysis, and it can assist in improving and optimizing the process. And this is basically not true for the energy analysis. And this figure is from this figure you can see that this figure represents the typical energy balance and exergy balance of any industrial process. If you look into the energy input and energy output only, you can see that the total input energy is equal to the total output energy. Whereas if you look into the exergy balance, you can see that the input exergy is higher than the output exergy. That means some exergy destroyed during the system due to the entropy generation. And you can also look into that the total input energy is higher than the total input exergy. That means whatever energy going in the system, they are not available. All of the energy are available. Some part of the energy are a non-available energy. Okay, that can be only be estimated when you do the exergy analysis of the system. Now, this is one of the most important figure for analyzing the sustainability of any system. If you look into this figure, here the x-axis basically represents the process exergy efficiency. Process exergy efficiency means as you increase the process exergy efficiency by some means, you can see that the sustainability of the process increases. At the same time, environmental impact, including the emission, is decreases. Okay. So if you somehow increase the process exergy efficiency, in that case, you can enhance the sustainability of the process. And this first figure shows here the Sankey diagram for exergy flow in any industrial process, where you can see that the total input energy is higher than the total output energy. That means some exergy destroyed during the process, and they are basically termed as the internal exergy loss or the system exergy loss. And at the output exergy part also, there are two components. One are the exergy of the useful products, whereas the exergy of the waste product. Since some of the products from the system may not be useful. Okay. Now, in the present study, following exergy indices are measured. First one is the internal exergy loss. That is nothing but the difference between total input exergy minus total output exergy. Whereas if you neglect the exergy of the waste product, in that case, that will give you the total exergy loss, which is the difference between total input exergy minus the exergy of the useful products only. Here we have omitted the exergy of the waste product. Similarly, if you look into the exergy efficiency, there are two types of exergy efficiency are there. One is the main product exergy efficiency, like that is the ratio between the main product divided by the total input exergy. Like in case of blast furnace, the main product is your hot metal. Similarly, in case of steel making, the main product is your steel. So if you that this ratio is basically the exergy of the main product divided by total input exergy, whereas second exergy efficiency is basically the exergy of the useful product. Here we have to consider the all the useful products also. Like in case of blast furnace, the blast furnace gas is also an useful product. Okay, so you have to consider that exergy also. Like in case of useful product exergy of the all the ratio between the exergy of the all the useful products divided by total input exergy, that will basically give you the exergy efficiency, useful product exergy efficiency. Now, exergy analysis can be useful for better utilization of energy resources. Okay, or you can say that energy resources as well as material resources, since both are associated with each other. And environmental impact like CO2 emission also associated with the energy resources. And CO2 emission from any system is not only produced by the combustion of fossil fuels that are required for the energy supply, but also due to the chemical reaction that are necessary to produce goods from the mineral resources. Like the best example of this is that the reduction of iron ore. For that, we have to supply the carbon for the reduction of iron oxide. And in that way, also CO2 is generated. Therefore, exergy analysis become crucial to reduce the emission due to the exergy losses during the operation. And since exergy analysis are widely used in the evaluation and optimization of chemical and metallurgical operations, various authors or researchers use exergy concept in the iron making and steel making also for their the process optimization. And several studies has been reported on the exergy analysis of conventional blast furnace, basic oxygen furnace steel making process, as well as the other steel making process like Corex BOA process or electric steel making process like that. And this table basically summarizes the recent study on the exergy analysis of various RN and steel making process. And if you look into this table, you can see that most of the researchers only focus on the exergy analysis of that system, like the electric arc furnace, sintering, or ladle furnace also. But very few researchers have analyzed the exergy as well as CO2 emissions together. On the other hand, if you look into the rotary hearth furnace based process like ITMK 3EF system, the only one researcher have reported the CO2 emission from that system, but no one till now have analyzed the exergy flow in the system. Okay. So therefore, there is a scope to analyze the exergy flow of the RHF EF route of steel making and then correlate the exergy with the CO2 emission for analyzing the sustainability of the RHF EF steel making system. Now, for analyzing the exergy flow of any industrial system, the knowledge of the material system is very much needed. Okay, otherwise you can't do the exergy analysis. And since rotary hearth furnace is still in development stage, therefore very few literature are available in literature. Therefore, we have to develop some suitable models so that we can analyze the material flow in the rotary hearth furnace. Therefore, the first objective is to develop suitable model based on the material and heat balance of rotary earth furnace as well as electric arc furnace separately for arriving the material and energy flow of the combined rotary earth furnace, electric arc furnace steel making process, and validate this model with the available literature data as well as if plant data is available. Then, based on the material and energy flow, estimate and analyze the exergy flow of the rotary earth furnace, electric arc furnace system combinedly, and they are basically named as FASMAT EF and ITMK3 EF. Basically, if the RHA product is DRI, in that case, the process is termed as the FASMAT EF, as I have already explained you. And if the rotary earth furnace product is nugget, iron nugget, in that case, the steel making process is known as ITMK3 electric arc furnace steel making route. Now, after that, compute and compare the exergy efficiency of this RHF-EF system together and also compare this efficiency to other steel making systems like blast furnace, basic oxygen furnace, as well as the porous BOA processes. And based on the material flow streams, develop a carbon balance model for the RHF-EF system and then estimate the CO2 emissions and then compare CO2 emissions values with other steel making routes. And finally, study the effect of potential parameters like escape addition in the electric arc furnace, then hot transfer of the RHF product like nugget or DRI to the electric arc furnace, and in-house power generation from the byproduct gases that are generated from the rotary arc furnace on the exergy efficiencies as well as CO2 emissions from the RHF EF system. Now, first coming into the rotary hearth furnace model. And if till now anyone have any query, then we can discuss here on, or we can discuss at the last.
We can discuss at the end. You can continue.
Okay, then. Now coming to the rotary hearth furnace model. For modeling of the rotary hearth furnace, basically we have divided rotary hearth furnace into the three zones. Okay, this figure shows you the typical schematic diagram of the thermodynamic model of the rotary hearth furnace. That, like in zone 1, as I told you that the rotary hearth furnace is divided into the three zones. In zone 1, basically composite pellet is heated from room temperature to 400 degrees centigrade, and the coal present in the composite pellet is decomposition of that take place in the zone 1 only. And in zone 2, basically heating of the volatile matter free composite pellet is occurred from 400 degrees centigrade to 900 degrees centigrade. And in zone 3, the main reduction reactions occurred, and after that the RHA product is heated to the exit temperature. Like in case of DRI, the exit temperature is 1250, but in case of ITMK3 temperature, the temperature is slightly higher, so that the nugget or gangue separation takes place. And like blast furnace, rotary hearth furnace is also a counter current reactor. That means solids and gaseous products are moved in opposite direction, so that the material and heat balance takes place efficiently. Okay, and this figure shows here the computation approach of the rotary hearth furnace model, like based on the input composition of the iron ore as well as a reductant toll. Initially, we have estimated the heat requirement in each zone. Like here, the delta H1 represents the heat requirement is in zone 1. Similarly, delta H2 represents here the heat requirement in zone 3, and delta H3 represents here the heat requirement in zone 3. Okay, and in zone 3, basically heat requirement comes to direct reduction, heat required for the direct reduction as well as heating of the reduced pellet up to 1250 degrees centigrade. and then this heat is supplied by the combustion of the external fuel. And based on the heat requirement in zone 3, basically the adiabatic flame temperature of the fuel is computed, and based on that how much air required for that combustion is also computed, and based on that the heat is supplied in zone 3. And and as I told you that the rotary hearth furnace is also counter current reactor. Basically, the whatever the hot product gases that are generated in zone 3, they are moved towards zone 2. And in zone 2, the heat requirement is supplied by the hot gases that are coming from zone 3 to zone 2, and from zone 2 to zone 1, gases are moving, and after that, gases are coming out from the rotary hearth furnace. And the model is capable of predicting the temperature drop in each zone after supplying the heat, as well as a volume and composition of the also product gases that are coming out from the system. And all the thermodynamic data, like the enthalpy requirement or adiabatic flame temperature calculation, they are basically computed by the FACSA software. Okay. And this figures table shows here the model prediction for the ITMK3 process only. And as I told you that initially we have computed the heat requirement in each zone, like in case of zone 1, zone 2, and zone 3. And based on the heat requirement in zone 3, how much external fuel is required, we have computed. Like in this case, the natural gas requirement is around 167 normal meter cube per ton of iron nugget. Okay. And and based on that, the model is also capable of temperature drop, like from zone 3 to zone 2. When gases are moving from zone 3 to zone 2, that is a temperature drop, like, and after that zone 2 to zone 1, and this temperature 313 represents here the exit gases temperature that are coming from the rotary furnace. And model is also capable of calculating the volume of the exit gases as well as the composition. And if you can see that the gases coming out from the rotary furnace is quite rich in CO as well as CO also. Okay, and if you calculate the calorific value of that exit gases coming out from the RHF, that has a quite high calorific value. That is more than 5,000 kilojoule per normal meter cube. And after that, we have also validated our model with the available data in literature. Like, and since very limited data is available in literature, we have validated our data with the ITMK3 process only, and we have computed that the coal requirement for per ton of nugget is 501, and reported is coal requirement is 500 kg only. Similarly, we have also compared the how much energy is supplied by the reductant coal as well as the external fuels also, and they are very much in uh, sync with the reported literature data. There is slight difference between the total input energy in case of the reported literature and our case. The main difference is the variation is due to that we have not included the power that is required, but in literature they have considered that also. And we have also validated the total CO2 emission per ton of nugget, and that value is close to 1.62 to 1.67 ton per ton of nugget. So we can say that our model gives us the satisfactory result, and we can use that model for the our analysis, exergy analysis. And these are the summary of the rotary hearth furnace model, like a thermodynamic model
Excuse
for
me,
the rotary
sir.
hearth. Okay.
In zone 3, have you considered the exothermic reaction, the energy coming from the exothermic reactions happen
Yeah,
during that?
everything has been considered, whether it is endothermic reaction or exothermic reaction. The
Okay,
total
okay,
summation gives you the net energy requirement in zone 3.
okay, okay, fine.
Now, these are the summary of the rotary hearth furnace model. Like, the thermodynamic model of the rotary hearth furnace has been developed and validated based on the limited literature data. And the model is capable of predicting the ore rate, that how much iron ore is required, coal rate, external fuel rate, exit gas composition and volume, including the sedimentation per ton of the RHA product for a given metallization percentage and external fuel gas. After that, we have also developed a electric arc furnace model separately, and that electric arc furnace model is basically developed based on the material and heat balance to estimate the material and energy flow of the electric arc furnace depending on the given variables and constant conditions. And based on the input and output mass system, the total input and output enthalpy can be computed. And this figure basically shows here the calculation scheme for the enthalpy balance of the electric arc furnace. Basically, you can see from this equation there are two components. One component is the heat supplier, and second component are the heat consumer. And in heat supplier has two components. One is the exothermic reaction that are occurred in the electric arc furnace, and second one is the electric energy required for the heating, melting, and dissolution in the electric arc furnace. And at the heat consumer part, one part is the heat loss and second part is the total summation of enthalpy of all the output streams that are coming out from the electric arc furnace, like crude steel, slag, electric arc furnace gas, as well as if any dust or fume losses are there. Okay, and these equations are basically solved simultaneously in the solvers of routine of the MS Excel to arrive into the material and enthalpy balance of the electric arc furnace model. And these are the constant conditions and operating parameters we have considered in the budget study. Like basic, we have maintained the basicity in the electric arc furnace like 2.5. Similarly, the FU percentage in the electric arc furnace is in the range of 25 to 30 degrees centigrade. And since we have validated our model with 100% DRI charging, initially we have not considered any scrap in the DRI, any scrap in the electric arc furnace, and we have also considered the total carbon input that are very much required for the carbon boil, or we can say the heat loss, the radiation heat loss. That is basically 35 kg per ton of crude steel. Similarly, the other operating parameters are mentioned here. And we've also assumed that the fume loss is around 10 kg per ton of crude steel and it contains FU only. And similarly, enthalpy loss considered in this model is the heat loss to the surrounding due to the radiation, conduction, convection, as well as heat loss in the cooling water. And in this model, we have not considered any burner fuel that is supplied to the electric arc furnace. That means energy is supplied either by the exothermic reaction or the electric arcing only. No burners are fitted in the electric arc furnace. And we have also considered the post combustion, and that is basically occurred by the CO that is generated due to the carbon oxidation, and which is around 15% with the furnace ingress air. And this table shows here the heat balance of the electric arc furnace for 100% DRI charge electric arc furnace. And these values can be easily computed by the thermodynamic software nowadays. And 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 if like in the right hand side table, you can see that the how much energy is consumed in the sensible heat carried out, sensible heat that is carrying with the crude steel as well as like exit gas and fume. We have calculated that value, and their summation gives around 621 kilowatt hour per ton of crude steel. And we have considered that the heat loss is around 25 degrees centigrade, 25 percentage. So the total heat consumed in the electric furnace is estimated around 828 kilowatt hour per ton of crude steel, and that is close to 3 gigajoule per ton of crude steel. Similarly, we have also computed the exothermic heat generated inside the electric arc furnace, like carbon oxidation, exothermic reaction, like slag formation. Slag formation, that means if the CO or SiO2 react, that is also exothermic reaction, and in this way also some amount of energy release. Apart from that, post combustion is also considered, but since we have considered that the DRI charge the electric arc furnace at 25 degrees centigrade, so there is no sensible heat of the DRI. In this way, the total exothermic reactions energy is computed as around 189 kilowatt hour per ton of crude steel, and by difference, the total heat consumed minus the heat generated due to the exothermic reaction, that will give you the total electricity required per ton of crude steel, and that comes around 638 kilowatt hour per ton of crude steel. Okay. After that, we have also validated our electric arc furnace model with the literature data. And for that, we have taken different types of DRI that are produced from different routes like Midrex process as well as HYL or Fastmet processes. And in literature and in our model, we have taken the same composition of the DRI for producing the crude steel in the electric arc furnace, and we have compared the reported electric energy per ton of crude steel with our model predicted electrical energy, and we have found that in all the cases the deviation is within the 6%. So we can say that the electric arc furnace model gives satisfactory result. After that, we have also validated our electric arc furnace model with the actual plant data. Okay, we have validated our model with two plant data. For plant A, basically 3 month data is provided by plant A, which shows various FE feed consist like hot metal, hot DRI, cold DRI, scrap, as well as the slag mix scraps also sometimes they charge as a scrap substitute. And therefore the model is modified to incorporate FE feed that is other than DRI, like scrap as well as hot metal, hot DRI, and slab mix scrap. And the composition provided by the plant for different input is fed in the electric arc furnace model, and the electricity consumption computed by model is compared with the actual plant data. And since percentage of post combustion and enthalpy loss is not mentioned in the actual plant data, therefore post combustion percentage is taken as same like 15%. And for validation of electricity consumption for month one, the percentage exergy or enthalpy loss is kept variable in the electric arc furnace model, so that the difference between the reported and model computed electricity consumption comes close to zero. And once that is done, after that, we have kept the same percentage of heat loss for the other month's data also, and we have computed the electricity requirement. And this figure shows here the comparison between the model calculated electrical energy consumption and actual electrical energy consumption for plant A, and we have found that the model gives satisfactory result. Okay. Apart from this, we have also compared the hot metal requirement, iron yield, burnt lime, slag volume, and composition from the model output as well as the plant data. And in these data also we found that the model gives the satisfactory result. Similarly, we have also validated our electric arc furnace model with the other plant data also. And for in other plants, basically they are operating with 4 different electric arc furnace with the different charging system. Okay, so in the same way as we have validated with plant A, we have validated our model with the plant B data also. And first figure here shows you the electric energy consumption compared between the actual energy consumption and model predicted energy consumption. And right side of the figure shows you the what are the slag volume, lime amount of lime requirement as well as the hot metal requirement uh, for the model as well as the actual plant data, and the computed electrical energy consumption, amount of hot metal, amount of lime, amount of slag and slag composition of, is then compared and with the provided plant data, which shows the reasonable match with the plant values. So we can say that the electric arc furnace model gives satisfactory result, and we can utilize that model for the exergy analysis purpose. Now coming to the exergy analysis of the rotary hearth furnace electric arc furnace process. Initially, we have separately estimated the exergy flow of the rotary hearth furnace and exergy flow of the electric arc furnace separately, and later we have coupled them together. And for analyzing the exergy of the rotary hearth furnace processes, the developed thermodynamic model of the rotary hearth furnace is used to estimate the input and output material systems like iron ore rate, coal rate, fuel rate, exit gas temperature, composition based on the given operating condition. And this table shows here the material, energy, and exergy flow of the phosphate process. And all these values are basically based on the per ton of the DRI basis, like for the phosphate process. And if you look into this table, you can see that for the production of 1 ton of DRI, we have to charge around 3.25 ton of the raw material. That includes the air blast, natural gas, coal, and ore. And if you look into the energy and exergy flow, input energy, you can see that the input energy is higher than that of the input exergy. But if you look into the exergy value of fuels like coal and natural gas, they are basically high quality fuels. In that case, you can see that the exergy value of the fuels are slightly higher than that of the energy value. This is mainly due to the exergy value contains the enthalpy value of the fuel plus the free energy of formation of those fuels also. That's why in case of fuels, the exergy value is slightly higher than that of the energy value. And in case of phosphate process, we have found that the internal exergy loss. You can see that the total input energy is similar to that of the total output energy. But in case of total exergy flow, the input exergy is higher than the output exergy. And this is balanced here because we have, by definition, we have minus subtracted the exergy of DRI and RHF gases that are from the total input exergy. In this way, we have get that total internal exergy loss is around 2.11 gigajoule per ton of DRI, whereas the total exergy loss is found to be around 2.89 gigajoule per ton of DRI. And main product exergy efficiency is 42%, whereas the useful product exergy efficiency is 87%. And similar analysis.
Excuse me, sir.
Okay.
Could you please repeat why in input side the exergy of the fuel is greater than that of the energy?
If you remember the exergy calculation part, where when we go for the exergy calculation of chemical exergy, that basically represents the free energy of formation of all the compounds of phases present in the steam. If you look into the energy part, basically in case of energy calculation, we only consider the calorific value of the fuel. Okay, that will basically give the how much energy is released when we only combust that of the fuel. That will give you the energy value. But in case of exergy, that will consider the energy value of the fuel plus the free energy of formation of that fuel also. Like if you take coal, the some energy is associated with the coal also. That if you dissociate that coal into that reference state, in that also you will get some amount of energy. That is also counted in the exergy value. That's why in case of fuels, basically XHG values are slightly higher than that of the energy value.
Okay, thank you.
Okay. Now coming to the XHG analysis of electric arc furnace process, like as I told you that initially we have did the XHG analysis for the 100% DRI charge electric arc furnace, and this table shows you the material energy and XHG balance of 100% DRI charge electric arc furnace, and all these values are mentioned per ton of the crude steel basis. Okay, and here you can see that to the per ton of crude steel we require more than 1 ton of DRI. Okay, that is around 1172 kg, and these are the minor element Fe, ferrosilicon, ferromanganese or lime. They are basically added for to maintain the composition or the basicity of the slag. And we have also considered that 2.25 kg of electrode is consumed per ton of crude steel, and these values are taken from standard literature. and you have to also supply some amount of oxygen and air blast. Okay, and in output part you can see that the crude steel exergy is found to be around 7.7 gigajoule per ton of crude steel. Okay, and here you can find that the total exergy loss or internal exergy loss is basically 1.11 gigajoule per ton of crude steel, whereas the total exergy loss is around 2.10 gigajoule per ton of crude steel. Here in case of electric arc furnace we have considered that the electric arc furnace slag is not a useful product, or as well as electric arc furnace gas is also not useful. That's why this value is increased from 1.1 to 2.1 gigajoule. And that's why that if you look into the main product exergy efficiency as well as the useful product exergy efficiency, both are same. That is 79%. That means in case of electric arc furnace, only crude steel is the useful product. Remaining part like slag and gases are the waste products. After that, we have coupled the rotary hearth furnace model with the electric arc furnace model to analyze the exergy following the combined RHF EF steel making system. And this Sankey diagram basically shows here the exergy flow of the fastmet EF steel making system. Fastmet, that means here we have considered the RHF product DRI. Okay. And in this case, for the combined RHF EF system, we have found that the internal exergy loss is around 3.59 gigajoule per ton of crude steel, whereas the total exergy loss is around 5.5 gigajoule per ton of crude steel, and main product exergy efficiency is 38%, whereas useful product exergy efficiency is 76%. But in case of electric arc furnace, we have found that we have to supply around 614 kilowatt hour of electricity per ton of crude steel, and in electricity production also substantial amount of exergy is destroyed. And if you consider that exergy loss also, in that case, the internal exergy loss is increased to 7.69 gigajoule per ton of crude steel, and total exergy loss is increased to 7.59 gigajoule per ton of crude steel. Similarly, the main product as well as the useful product exergy efficiency are decreased. Like main product exergy efficiency decreased to 32%, whereas the useful product exergy efficiency decreased to 61% only. Okay. And similar analysis has been conducted for the ITMK3 EF system also. Like in case of ITMK3, the RHF product is nugget, and here we have found that the total exergy loss, including the exergy loss and power generation, that value is 5.12 gigajoule per ton of crude steel, and total exergy loss is around 7.99 gigajoule per ton of crude steel. Whereas the main product exergy efficiency 33%, whereas the useful product exergy efficiency 66%. If you look into this ITMK3 EF system and Fastmet EF system, that in case of exergy loss in Fastmet EF system is higher than that of the ITMK3 EF steel making system. The main reason behind this is that in case of ITMK3 EF system, the electricity requirement in the electric arc furnace is quite low. This is only 370 kilowatt hour per ton of crude steel, whereas in case of Fastmet EF system, the electricity requirement is around 614 kilowatt hour per ton of crude steel. That's why this value is lesser in case of ITMK3 EF system. Now, after that, in from these two figure, you can see that the chemical exergy value or the total exergy value of the RHF gases that are coming out from the both the RHF EF system is greater than 7 gigajoule. Okay, and for the ITMK3 EF system also, as well as the Fastmet EF system also. And if we analyze the calorific value of the RHF product gases, it is found that it is more than 5,000 kilojoule per normal meter cube for the ITMK3 EF system, and it is rich in CO gas, as I already mentioned earlier. And also the chemical exergy of the RHF product gas is 7.54 gigajoule per ton crude steel for the ITMK3F system, and that can be further utilized in in-house power generation, so that we can reduce the dependency on the uh, requirement of electricity on the power grid. Okay, and considering 35% power generation efficiency of the turbine, the total energy consumed to produce the electricity required for the ITMK 3A system, which is 370 kilowatt hour per ton crude steel, is around 3.8 gigajoule only. Okay, that means still there are 3.754 gigajoule of energy available after producing electricity that is required for the running the system. And but in case of integrated iron and steel making system, around 3.5 gigajoule energy also required for the downstream processes like heat treatment or rolling process. But after producing electricity, the remaining energy in case of ITMK 3F is 3.75 gigajoule, which is higher than 3.5 gigajoule. So we can say that there is still the required energy is left to run the steel making system smoothly for the downstream process. Okay. Similarly, calculation has been conducted for the Fastmet EF steel making system after partitioning the 3.5 gigajoule per ton of crude steel exergy for downstream processes. And figure A shows here the exergy flow for the ITMK3 EF system, or figure B for the Fastmet EF system. And after that, we have analyzed the exergy indices again, and we have found that the total remains same for both the cases. Either you will do the in-house power generation or you can take the electricity from the outside. But the main product exergy efficiency is increased for the ITMK3F from to 40% from the 33%. But in that case, the useful product exergy efficiency decreased to 59% from 66%. The main reason is for this decrease is that the useful gases that are coming out from the system is again recirculate for the in-house power generation. That's why the useful product exergy efficiency decreases here. Similarly, in case of Fastmet EF system, the main product exergy efficiency is increased to 37% from the 32%, whereas useful product exergy efficiency is decreased to 54% from the 61%. And as I initially told you that the most of the steel till now produced through the conventional blast furnace basic oxygen furnace process. That's why for comparison purpose we have also examined the exergy flow in the conventional blast furnace basic oxygen furnace process. And this figure shows here the process flow in the blast furnace basic oxygen furnace process. Like the in case of this process, basically initially iron ore is converted to sinter in the sinter plant, and sinter as well as some amount of iron ore is charged in the blast furnace. Similarly, coking coal are converted to coke in the coke oven and they are charged in the blast furnace, and some PCI is also injected there. And in some plants, the pellets are also charged in the blast furnace, but we have not considered that the plate charging in the blast furnace. And then the hot metal that are produced in the blast furnace, they are basically refined in the basic oxygen furnace process, and then we will get the crude steel. Okay, and in basic oxygen furnace, to counter the exothermic heat that are generated, some amount of scrap is also charged. Now, for analyzing the exergy flow in the blast furnace, a thermodynamic model that are developed earlier by the some other team member is utilized. And this table shows here the material energy and exergy flow of the blast furnace, and all these values are basically per ton of the hot metal basis. And this table shows here the constant condition they are considered for the blast furnace operation, like the select basicity is maintained at 1.15 to 1.16, and similarly the FU and select is considered 0.6, like that. Okay, and we have fixed that the iron ore charge in the blast furnace 470 kg, and remaining iron feed is required charged by the sinter. Similarly, oxygen enrichment in the air blast is 1.5 uh, percentage, and the variables of the blast furnace model is sinter and coke, and output of the model gives you the air blast, like blast furnace gas volume and composition. And here we have considered that the heat loss in the blast furnace is 0.5 gigajoule per ton of hot metal, and that is their objective function. And we have found that in case of blast furnace, the internal exergy loss is around 1.71 gigajoule per ton of hot metal, and total exergy loss is around 2.19 gigajoule per ton of hot metal. And main product exergy efficiency comes around 55%, is while useful product exergy efficiency is 86%. Okay, and these exergy indices values are in coincidence with the results that are reported in literature by Liu and their team. And for analyzing the exergy flow in the basic oxygen furnace process, basically we have modified the electric furnace model that is developed earlier. And in place of electricity requirement, is amount of scrap required to counter the exothermic reactions happen inside the basic oxygen furnace is estimated. And the equations that are generated based on the material and enthalpy balance are solved simultaneously, similar to that of the reactor furnace in the MS solve Excel. Okay. And the variables of the basic oxygen furnace model is hot metal that is require pattern of food crystal as well as scrap and lime. And the output of the model basically give you the oxygen required for the process, the select composition and volume as well as view of gas composition. And this figure shows you the calculation scheme for the head balance of the basic oxygen furnace process. Like electric furnace, here also the two components were there. One is the heat supplied components part, and then another one is the heat consumed. And here the heat supplied is basically either the exothermic reactions that are basically occurred in the basic oxygen furnace. Otherwise, here the delta H1 is basically represents here the sensible enthalpy of the hot metal that is basically charged in the basic oxygen furnace that are basically transferred from blast furnace to the basic oxygen furnace process. And in the heat consumer part here is similar to that of the electric car furnace, like heat loss as well as the sensible enthalpy of the all the output products that are coming out from the basic oxygen furnace, like crude steel, slag, or gases. And this table shows here the constant condition of the basic oxygen furnace process. And this Sankey diagram basically represents the enthalpy balance of the basic oxygen system per ton of crude steel. And per ton of crude steel, basically total input energy is around 2.29 gigajoule per ton of crude steel. And this table shows here the material and energy and exergy flow of the basic oxygen furnace per ton of crude steel. And it is estimated that to counter the exothermic heat required generated in the blast furnace, we have to charge around 113 kg of scrap. Okay, that is around 10 to 15% of the total input material. And in case of BOF process, we have found that the internal exergy loss is around 684 megajoule per ton of crude steel, and the total exergy loss is around 1 gigajoule per ton of crude steel. And here the main product exergy efficiency is 80%, and whereas useful product exergy efficiency is 89%. Apart from that, as I already shown you in the process flow of the integrated blast furnace basic oxygen furnace process, there are sintering plant is also there and coking plant is also there. In the production of sinter and coke, some exergy is also lost, and we have to consider that exergy also, so that we can truly compare the RHAPF system with the blast furnace basic oxygen furnace process. But we have not developed the sintering model as well as the coking model, but how much exergy can be destroyed in the sintering and coking process can be taken from the literature data. And for our calculation, we have found that the per ton of crude steel production, we need 1136 kg of sintering, and whereas we need 323 kg of coke. And remaining, since there are PCI is also injected there around 170 kg, that's why the coke rate is slightly low. And in that case, we have found that for the production of 1136 kg of sinter, the internal exergy loss is around 1.40 gigajoule and total exergy loss is around 1.83 gigajoule. Similarly, for the production of 323 kg of coke, the internal exergy loss is estimated as around 1.09 gigajoule and total exergy loss is around 1.21 gigajoule. And when we combine all the process together, like coke oven, sintering, blast furnace, and basic oxygen furnace, that will give you the integrated exergy flow in the and BF system. And this figure shows here the exergy flow of the combined BF steel making system, including the coke oven as well as the sintering. And for that, we have found that the internal exergy loss is around 4.29 gigajoule per ton of crude steel, and the total exergy loss is around 7.01 gigajoule per ton of crude steel. And main product exergy efficiency is 37%, whereas useful product exergy efficiency is 87%. After that, we have compared the exergy indices of the blast furnace with the rotary hearth furnace steel making systems, as well as we have, for comparison purpose, we have also considered the exergy indices of the data that are reported in the literature for the BFBF system as well as the other steel making processes, like the Corex Dual Fruit as well as the 100% scrap charge electric arc furnace system. And it is observed that the exergy indices of Corex based steel making process are inferior to exergy indices of BFBF as well as RHAPF system. From this figure, you can see that these are the values of the Corex BOF route. Okay. And the right hand side of this figure basically represents the results of the present study. Then the exergy indices of ITMK3 EF steel making process are found to be superior to Fastmet EF steel making system. From this figure, you can see that these values are for the Fastmet EF system and these values for the ITMK3 EF system. And you can see that the exergy indices of ITMK3 EF system are slightly superior to that of the Fastmet EF system. And if you compare the main product exergy efficiency of BF process, and this value that is basically better than both the variants of RHPF systems, like the Fastmet EF and ITMK3EF system, but the useful product exergy efficiency is comparable, and the calculated main product exergy efficiency of both BF process become comparable if the RHP product fuel gases are utilized for the in-house power generation. Okay, if you look into this values with right hand side of these values, okay, in that case they will become the comparable. After that, we have also analyzed the effect of scrap ratio and hot DRI charging in the exergy indices of the Fastmet EF system. And this figure, these both figure are for the Fastmet EF system. And here the top line is basically represents the variation of total exergy loss when we increase the scrap ratio. And these two lines are basically for the 600 degrees centigrade and 800 degrees centigrade. And for comparison purpose, we in this figure we have also included the BF process, and the right hand side figure basically shows you the exergy efficiency. Okay. And it is observed that the exergy indices improve with increase in scrap ratio and hot transfer of temperature. Like you can see that if you increase the scrap ratio, the exergy efficiencies are increasing as well as the total exergy loss is also decreasing. And as we increase the hot transfer ratio, that means initially we have considered that the DRI is cooled to room temperature and again heated and melted in the electric furnace. But in place of that, if somehow we can transfer the product RCF product, either DRI or nugget at the hot condition from 600 and directly transfer to the electric arc furnace, in that case we can further improve the exergy efficiency of the system. However, in case of BF system, you can see that there is a limitation of the scrap addition. You cannot add more than 20% scrap in the BF system. But nowadays, the modified BF systems are there. They are basically termed as a Tenova process, where there is a facility of melting, arcing is also there. Facility of melting of the scrap is also there. So there, in that case, you can increase the scrap percentage in the modified BOA process. And where for comparison purpose, we have considered that also, and we have found that if you increase the scrap percentage greater than 40%, in that case, exergy indices of Fastmet EF steel making system become comparable to that of the BF process if DRI transfer temperature is higher than 800 degrees centigrade. But in the case of ITMK3 EF system, similar analysis has been conducted for the ITMK3 electric arc furnace process. In that case, we have found that the exergy indices improve with increase in scrap ratio and hot transfer temperature similar to that of the Fastmet EF system. But the exergy indices of BF process are found to be comparable to the ITMK3 system if nugget transfer temperature is around 800, it should be 600 degrees centigrade. From this figure you can see that at 600 degrees centigrade they are comparable. Okay. And at higher scrap ratio, if you go for higher scrap ratio more than 40%, uh, exergy indices of ITMK3 EF steel making system becomes superior to the modified BF process if nugget transfer temperature is greater than 600 degrees centigrade. And the exergy of powdered gases, like if you look into this figure, exergy of the powdered gases of the ITMK3F process are always found to be better than that of the blast furnace basic oxygen furnace process. Now coming to the summary of the exergy analysis, the exergy values of the DRI and nugget are found to be 6.67 gigajoule and 8.01 gigajoule per ton of the product. Now you can see that the exergy value of DRI is lower than that of the nugget. The main reason behind this is that in case of nugget there is no gang associated with the nugget, while in case of DRI the gang associated with the ore as well as the coal both are remains in the DRI. That's why this value is lower for the DRI. And exergy indices of ITMK3 EF steel making process are found to be superior to that of the Fastmet EF steel making system. And by utilizing the excess RHF ported gases for in-house power generation to reduce the dependency on the power grid, the main product exergy efficiency of the RHF steel making system are improved at the cost of the useful product exergy efficiency. And at a lower scrap ratio, the exergy indices of the blast furnace basic oxygen furnace steel making route become superior to both the variants of the RHF steel making process. Moreover, as the scrap ratio increases, the difference in the exergy indices between these two routes are decreases, and further at around 50% scrap ratio, the total exergy loss as well as the main product exergy efficiency for the modified BF or we can say BF Tenova modular furnace process becomes comparable to that of the RHPF process. And when hot DRI or nugget is transferred to the electric arc furnace from rotary arc furnace, exergy indices of the RHA making system further improves. However, that the exergy indices of BF steel making process remain superior to that of the phosphate EF steel making systems, even after hot transfer of the RHA product to EF at 800 degrees centigrade. And at higher scrap ratio, that is greater than 40%, exergy indices of RHA steel making systems becomes comparable or superior, depending the RHA product to the that of the BOF modified BOF process if the RHA product transfer temperature exceeds 600 degrees centigrade. After that, we have analyzed the CO2 emissions from the RHF EF system. And for analyzing the CO2 emission from the RHF EF system, basically, we have analyzed the net carbon flow in both the variants of RHF EF system, and that are basically examined based on the material flow that are coming from the developed thermodynamic model. And the primary carbon sources of CO2 emission in RHF are basically the reductant coal and the carbon that are present in the natural gas. And whereas in case of electric arc furnace, the main carbon sources of CO2 emission is equivalent fuel required for power generation. And we have considered that the Indian grid factor that is around 0.8 kg CO2 per kilowatt hour, or we can say that 0.21 kg of carbon per kilowatt hour of power generation. And the net carbon input is computed by utilizing this equation, that is basically the summation of total carbon input plus equivalent carbon for electricity generation minus carbon that is present in the crude steel minus equivalent carbon recovered, if any. Okay. And the net carbon CO2 emission has been estimated by converting this net carbon into the CO2 completely. And these two figures shows here the carbon flow for the RHF EF steel making system, figure A for the ITMK3 EF system, and figure B for the phosphate EF system. And in case of ITMK3 EF system, we have estimated that the net carbon input is around 524 kg per ton of crude steel, whereas in case of phosphate EF system, the net carbon input it was slightly higher, that is around 550 kg per ton of crude steel. And if you convert this net carbon input into CO2, it comes around 2 ton of CO2 per ton of crude steel. Okay. And if you introduce the in-house effect of in-house power generation on the CO2 emission also, in that case, we have found that the net carbon input is slightly decreases for both the cases. And net CO2 emissions for the ITMK3 EF system is decreased to around 1.6 ton, whereas in case of phosphate EF system, this value is decreased to 1.1.7 ton per ton of crude steel. That means the total CO2 emission is reduced to around 300, 275 to 300 kg per ton of crude steel for the RHF system. After that, we have also analyzed the effect of hot transfer of the RHA product to EF and scrap ratio on the CO2 emissions. And this figure shows you the CO2 emission for the various operating parameters like the effect of scrap ratio as well as the hot transfer of the RHA product and DRI. And for a typical value of 50% scrap charging in the ITMK3 as well as phosphate process, the total CO2 emission value is decreased from around 2 ton to around 1.12 ton only. Whereas if you look into the effect of hot transfer temperature, you can see that for the 800 degrees transfer temperature, the CO2 emission value is decreased to 1.82 to 1.87 ton per ton of crude steel. That means the effect of escape ratio is quite high compared to that of the hot transfer temperature in case of CO2 emission values. After that, we have also compared the CO2 emission value of the phosphate EF system with other steel making systems that are basically reported in the literature. And here the first three figure basically shows here for the BF system, second one for the Corex BF2, and third one for the rotary kiln electric arc furnace system for the steel making. And these values are for the mid-dex route of steel making. And this the slide value green color value shows here for the 100% sculptured electric arc furnace system. Okay. And it is well known that the maximum applicable scrap ratio in the BF is 20%. And if we compare the CO2 emission for the 20% scrap ratio with the blast furnace basic oxygen furnace process, we found that the CO2 emission from the RHF AF system as well as the ITMK3F system is lower than that of the conventional blast furnace basic oxygen furnace process. Now coming to the summary of the CO2 emission analysis. In case of ITMK3 as well as phosphate EF system, the net CO2 emission has been found around 2 ton per ton of crude steel, and that value is comparable to that of the conventional blast furnace basic oxygen furnace process. But for the same scrap ratio, the CO2 emissions values of the RHF system are found to be lower than that of the BF process. And the net CO2 emission per ton of crude steel when excess RHA product fuel gases are utilized for in-house power generation, are found to be around 1.61 ton for the ITMK 3EF system, and that value is for 1.74 ton per ton of crude steel for the phosphate EF system respectively. And with increase in scrap ratio in EF and hot transfer of the RHA product gas to electric arc furnace, the CO2 emission from the RHA EF system may further decrease. Now, finally, we have also analyzed the sustainability of the RHF system. And initially, I have told you that the main sustainability parameters are the comparison between the CO2 emission and the exergy efficiency. And somehow, if you increase the exergy efficiency, the sustainability of the system increases as well as the CO2 emission value decreases. And that is seen in this case also that then, and for comparison purpose, in this figure, we have also included the correct wave route that are basically the triangle here, red and black triangle shows here for the correct wave route, and this square figure, these two square figure here, the red color basically shows here the main product exergy efficiency, whereas the black color, uh, black dots basically represents here the full product exergy efficiency. And for comparison purpose, we have also included the scrap charge electric furnace exergy efficiencies values. And it is found that if the main product exergy efficiencies are improved by some process redesign, in that case, the CO2 emission per ton of crude steel for the both the variants of RHF EF system are decreased. You can see that from 1, 2, and 3. Okay. The except some cases, the main product as well as main product exergy efficiency as well as the CO2 emission values of RHF EF system are found to be better than the BA steel making process, and these two sustainability parameters are always found to be better than correct route of steel making system. You can visualize this from this figure. And the present work makes the beginning to analyze the environmental sustainability of the RHF system and set a path for future research in that direction in more detail, including the economics, since we have not included the economics in our present study. Now coming to the major conclusions and some scope for future work. Now first major conclusion on the efficiency are that it is found that the exergy efficiencies of the ITMK3 EF steel making system are superior to that of the phosphate EF system in respective of all the cases studied. And exergy indices of RHF EF steel making system are superior to the correct BOF process, but in contrast, these are either comparable or superior depending on the RHF product to the conventional BOF steel making system, especially with the hot DRI charging and scrap addition. And in case of CO2 emissions, the major conclusions are that without any process flow modification like 100% cold charging of the RHA product to the electric furnace, the net CO2 emission are found to be around 2 ton per ton of crude steel, and which are comparable to that of the conventional blast furnace basic oxygen furnace process, but with the process flow modification like scrap charging and hot product transfer of the RHA product to the electric furnace, emission values are decreased to 1.6 ton per ton of crude steel estimate approximately, which are basically 16 to 20% lower than that of the conventional blast furnace basic oxygen furnace process. Now the major conclusions on the process sustainability are like it is demonstrated that the with process flow redesign, CO2 emission value and exergy efficiencies of RHA steel making system can be found to be better than that of the conventional blast furnace basic oxygen furnace steel making process. And these two sustainability parameters are always found to be better than correct route of steel making. However, process redesign lowers the emission without marked improvement in the exergy efficiencies because of the lower calorific value of the fuel gases that are coming out from the system. And the RHF-EF route scores highly in the sustainability index, which are conducive to its favorable implementation in industry, especially with the higher scrap ratio and hot transfer of the RHF product to the electric furnace. And for future development of the RHF-EF process should aim towards the improvement in power generation efficiency and with utilization of renewable electrical energy in RHF-EF system, which should further help in reducing the input exergy attributed to the electrical energy requirement and thus improve the exergy indices and CO2 emissions from the RHPF systems. And these are the few limitations and scope for the future work. Like in the present study, we have validated our RHF model with the literature data only, but it is always advisable that the model should be validated with the actual plan data. Therefore, attempts should be made to validate the model data with actual plan data whenever applicable. And since the availability of the natural gas is not similar worldwide, Therefore, the effect of fuels other than natural gas like coke oven gas or some fuels which are richer in hydrogen may be analyzed on exergy efficiencies and CO2 emissions for the combined RHF-EF system. Apart from this, the effect of the degree of metallization of DRI and varying burden quality on exergy indices and CO2 emissions from the RHF-EF steel making system can be analyzed. And since presently most of the DRI is produced either through the matrix route or rotary kiln, especially in Indian scenario, therefore the exergy efficiencies and CO2 emissions from the rotary furnace, electric furnace route can be compared with the mid-rex EF route of utilizing the either natural gas or coal gasification as input, as well as rotary kiln DRI EF route of steel making, using various quantities of scrap in EF to examine the role of circularity in the steel making. And these are the composition of the various input and output streams for the fast-made EF system. Like similarly for the composition of the input and output system of the ITMK3 EF system. And these are the for the BF systems. Okay. And these are the major references of the present work. Thank you everyone for this. Okay. If now, if anyone have any doubt, I would love to clarify those.
I have a question.
Okay.
Now it seems that the Corex plus BOF, if you do this exergy analysis for this combination, then you
Okay.
said rotary hot furnace plus EAF is better.
Okay. Yes.
But what about HYL plus EAF? If you compare that with rotary hot and EAF.
Okay. That's why I have told you that this basically our model is compared with the blast furnace as well as the whatever data basically reported in the literature, like the exergy flow of the correct route of steel making are reported. That's why we have compared that value. But since the HYL, EF as well as the matrix EF route, they are basically not reported that. So you cannot directly comment that the RHP is either superior or not to that. For that, we have to analyze the HYL, EF route, exergy indices of that route also. Okay. But since it is reported in literature that the exergy efficiencies of the Corex EF route as well as some other routes also, like escape charging, 100% escape charge electric furnace route as well as the blast furnace basic ocean furnace process. That's why I have comment on that the RHPF route is superior to that of the Corex route of steel making. But without analyzing the HYL EF route, it is very difficult to comment that what are the exergy indices of the RHF system.
Okay. And I have one more general question.
Okay.
What is the advantage of rotary arc furnace over, suppose I have a conventional furnace having the counter current solid gas reaction? What
Okay.
rotary arc furnace, what kind of advantage it will give? Or it will be same?
Advantage of rotary hearth furnace is that in rotary hearth furnace we are charging the composite pellet. Composite pellet are basically made from the mixing of the iron ore fines and non-coking coal fines. Okay. And in that case, the reaction rate is quite faster. Okay, compared to if you compare to that of the rotary kiln process of DRI making. Okay, and in this way you can, and also you can utilize the inferior quality of the non-coal for the production of DRI.
Okay.
And also in case of DRI, it is dual, as I already told you that they are basically dual fuel in nature. Dual fuel means coal, carbon present in the coal is utilized as a reductant as well as the other fuel gases. Like in my case, I have considered natural gas uh, as a energy supply that is required for the endothermic reaction, that a heat demand for the energy. So in this way, you can take other fuels also which are richer in hydrogen, like coke oven case also.
Okay. Okay. Right. Any other question from participants? Okay, Harsh Kumar, you can ask your question.
Good afternoon, sir. I have a very simple question that where do we charge coal fines and natural gas in rotary hearth furnace, and how does the hot gas moves inside through the three zones?
Okay, basically, if you look into the rotary earth furnace, okay, basically composite pellets in shape wise, composite pellets are similar to the iron pellets. They are basically made in the pellet plant. The only difference is that in case of iron pellet, we are not mixing any fuels or reductant. But in case of composite pellet, the iron ore is mixed with the non-coking coal fines. So as a reductant, and they are basically pellets are made outside the rotary hearth furnace, and after drying they are charged in the rotary hearth furnace. And its name suggests that the in rotary hearth furnace the hearth is rotating, and the whatever pellet we are charging in the rotary hearth furnace, they are kept stationary in the hearth, and hearth is rotating. Okay, and hearth is moving in one direction, and 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 the and when you combust the fuels, if you look into this figure, okay, just a minute. If you look into this figure, that the in case the combustion is take place, basically majority of the heat demand is required in the zone 3 where the reaction takes place, so the endothermic reaction takes place. So we supply the or combust the fuel in the zone 3 only by supplying the external burners or and air, and those hot gases are moving from zone 3 to zone 2 to zone 1. Okay, but the charging is take place from zone 1 to zone 2 to zone 3. In this way, the earth is rotating from zone 1 to zone 2 to zone 3, and after zone 3 the DRI is coming out from the rotary earth furnace process, and this is a continuous process. Okay, and combustion is take place in zone 3. So the hot gases are moving from zone 3 to zone 2 and zone 2 to zone 1, then coming out from the system. In this way, they are basically the counter current reactor, and that's why the material and heat enthalpy exchange between the solid and gas take place.
Okay, sir. Thank you.
Any other question? Okay, there's no question now. So let's conclude this session over here. So we are very thankful to Dr. Binay Kumar for accepting our invitation and giving this talk and giving this wonderful, very informative uh, presentation over here. Thank you so much, sir.
I would like to thank all the coordinators from the Department of Metallurgical and Materials Engineering, NIT Rourkela, especially Dr. Dinda, for inviting me to present my work in this short-term course on grease steel making industry 4.0. Thank you once again from my side.
Welcome. Okay, we'll have
Then,
break of. Yes, sir.
then can I leave now? Okay.
Yes, sir. Thank you so much.
Okay. Thank you very much.
Okay, so we'll have break of 10 minutes. Next session, not 10 minutes, 5 minutes. And next session will start at 4 o'clock. Next speaker is Dr. Deepu Kumar from IIT. So we'll meet at 4 o'clock. Hello, Professor Deepu Kumar. Can you hear me?
Hi, yes, I can hear you. Hi, how are you?
Okay, we'll start. You're ready? Shall we start?
Yeah, so it would be useful if you can give me background of attendees. Are those just,
Uh,
from industry, from
Most
some
of them are
students, or
PhD scholars. Few are them from industry also, but
yes.
mostly MTech and PhD students.
Okay, thank you.
Okay, so uh, I welcome all the participants to this last session of the day. The speaker for this session is Dr. Deepu Kumar. Uh, Dr. Deepu Kumar is currently working as assistant professor in Department of Metallurgical Engineering and Material Science at IIT Bombay. He is also associated with the Center of Excellence in Steel Technology at IIT Bombay. He did his PhD from Carnegie Mellon University in 2018 in the area of secondary steel making and clean steel production. He worked for a year at the Praxel Technology Center, uh, Toronwanda. I guess I'm pronouncing it correctly. In New York. After his PhD, his research expertise include primary and secondary steel making, clean steel production, characterization of inclusions, and high temperature experiment involving metal, slag, and refractories. He had extensively worked on the application of backstage, K-map, automated inclusion analysis, laboratory scale induction furnace, and high temperature confocal laser scanning microscope in steel making. He is also exploring research opportunities in sustainable solutions for iron and steel production, hydrogen-based iron making, and e-waste recycling. Dr. Kumar has published more than 30 research articles in peer-reviewed journals and international conferences. He teaches courses on transport phenomena, steel making, and the kinetics of high temperature processes. So with this brief introduction, I welcome Dr. Deepu Kumar for this session to deliver a talk on strategies for reducing CO2 emission during steel refining. It's over to you now, sir.
Thank you, sir. So can you see my screen?
Yes, it is visible.
Okay. So since this is last talk, so I'll be between the attendees and whatever plans after the workshop is. Anyway, so I'm sure as part of this workshop, you would have seen many iron making related talk where, when we talk about green steel production, people generally talk about nowadays hydrogen reducing ore hematite using hydrogen or application of hydrogen for DRI productions and or injecting it in blast furnace and such so on. However, there is strong case for using reducing CO2 emissions during steel refining as well. Not only that, whenever even if you produce DRI which is solid using hydrogen, you have to melt it as well. So there is a we need to also research a lot of or do a lot of experimentations or model development or whatever calculations to ensure that we are ready for processing those DRI as well. However, I'm not going to talk about DRI today. I'll talk about something conventional steel making, something about conventional steel making, and some strategies for reducing CO2 emissions, and I'll go in a little bit depth about in this. I hope I'm still this. You can still see my screen, right?
Yes, yes.
Yeah. Okay. Uh, so I'll go a little bit depth about what appears to be simplistic calculations can be used to strategize a lot of things in the steel making itself. So I'll start with the steel making overview and then some process description of BOF, which I'm sure most of you know already. But we'll go a little bit depth about how we can develop a static model that can be used to calculate or look at some scenarios for potential CO2 emission reduction. So before I do that, here's an overview of what I do generally. Most of that is covered in the introduction. So, so primarily I work in three verticals. One is experimental part, where primarily it's high temperature experiments covering uh, all the way from DRI production to steel slag gas reactions or recycling, and also look at the refractories applications as well. And recently, I'm also working on a project on metal matrix composites, uh, development of new material for that. Then the second vertical is related to modeling, primarily using thermodynamic tools such as FactSage, and some of those things I'll discuss in today's talk as well. Now we are also working on integrating FactStage and ChemApp with Aspen Plus for large scale simulations. We have also done some modeling related to heat and mass transfer models for high temperature processing, including well annealing furnaces. On the characterization side, we have a high temperature confocal laser scanning microscope, which can give you about half micron resolution at temperature as high as 1700 Celsius. So we can do a lot of steel phase transformations or phase transformations involving metals or ceramics. The interactions between different metals or melts, including steel, and then let's say steel slag reactions, we can look at live in this microscope, or slag refractory interactions and so on. So this is the unique facility, the only one publicly available in India. The second is the automated feature analysis using a FPGA facility that we have. So in this case, is primarily we use it for particle analysis or inclusion analysis in steel, but there are several other applications one can use it for. So this gives you a large data set regarding defects or inclusions in steel, and that can be correlated with the process. We also have a setup for electrolytic extractions for inclusion analysis in steel, but it can again be used for other alloys as well. So just very simple steel making. By steel making, I refer here whatever we get after blast furnace operation. So we essentially get hot metal, but nowadays the other type of processes contribute significantly to the production of steel, which includes scrap-based processes such as electric arc furnaces and induction furnace as well. The primary function is to remove carbon, silicon, manganese, and phosphorus type impurities. And during the process, since you have these impurities, when you try to remove primarily using oxygen, you generate significant amount of heat. So you can add other iron-bearing additives such as plant metallic waste, such as mill scale or discards, and you can also add DRI or ore and so on. The processes that are available are BOF, which is the most popular and most commonly used. Other ones are electric arc furnaces. Then Konark is also there in India in many plants, with I think both Tata Steel and JSW and probably MNS as well. Konark is essentially converter plus arcing both. That essentially allows, so BOF is primarily hot metal based, EF is primarily scrap based process. Konark allows you to optimize your supply of hot metal, liquid hot metal, and the scrap, so you can use energy from arcing in addition to the chemical energy from the converter process. There is another one which is called energy optimizing furnaces. There are only few left in India and still not used as energy optimizing furnace. But the concept was quite novel, that you can use the off gas from the primary steelmaking process to preheat the scrap and feed it back. There's other one which I missed to mention, and which we very often also we don't talk about, is also the induction furnace, which contributes a lot to our steel production capacity. To about, I think, at least a third of the production or so is from the induction furnace, and those are relatively small scale. Not so small scale nowadays. I mean, you have 30 ton to 50 ton. 30 ton is quite common, not so small. And overall it produces about 40 million ton or so in context. So induction furnace, we should also talk about it a little more. Nevertheless, today's talk is primarily on the BOF steelmaking, and here the requirement is the removal of impurities, the appropriate tap temperature, and we are very often concerned about the yield of the process, that essentially is related to the FeO concentration in the slag. And the tap to tap time, as you can reduce the tap to tap time, you can also increase the productivity of the slag. So typically the BF operator would control the lance profile, that is how far you are from the melt. So soft blow versus hard blow. So if you are away from the melt, then it's a soft blow, and if you're closer to the melt, then it's a hard blow. Then the post combustion, which is again not very frequently practiced in Indian scenario, as far I know. I may be wrong, but that again is quite important for the utilization, energy utilization, as we will see a little later. Operator also controls the flux injection, whether to add fluxes such as lime, dolo lime at once, or continuous additions and so on. Then the coolant injection. By coolant, because this removal of these impurities generate lots of heat. So you can add coolant such as iron ore or scrap or DRI or some plant level waste such as mill scale briquettes and so on. As an operator, let's say you start from here. So that is high carbon, low temperature, and you go till here. So you can start with as low as 1400, and the tap could be 1650. And the carbon you can start with about 4.3%, and tap at as low as 0.03 or so. So if this is the target, as an operator, you would like to start here and directly reach here, which is very often impossible. You can have some simple mass balance, heat balance calculations, and that's this large box, which is essentially the static controls, overall heat and mass balance. You can hit this window. This window means the temperature can vary from this to this range, and carbon can vary from this to this. Nowadays, many plants, even again in India as well, Tata Steel has some plant as well as JSW, maybe other places as well. They use sublance, and if you have sublance, then you can make intermediate measurement about the temperature and carbon concentrations and so on. And if you are, let's say, going here, this could have taken you to this, still in this box somewhere. But if you can make a course correction, you can correct from here and hit this smaller box, which is dashed region. So that is very significant improvement, and such control actually allows to improve productivity and reduce losses. But it requires intermediate sampling, investment on sublance, and more important, of using sublance in appropriate manner, which very often appears a challenge for the operator. That's about the dynamic model. That's the dash line. It's strictly not a dynamic model, but it's sort of application of dynamic model, but it is dynamic controls. But today's talk is primarily focused on static model and look at its application. So if you talk about a static model, the first component is just a simple mass balance. So if this is your this box represents the converter, then you add hot metal, scrap, fluxes, mill scale briquettes, and so on. And into that mixture, of course, there's no direct all the addition at one time, but overall this addition is again augmented by the oxygen lance. So you have those CD nozzles, you supply oxygen at very high flow rate, and finally what you get is top gas, slag, and steel. In addition to the top gas, carries dust or sludge as well, which has very often significant amount of iron or sometimes zinc as well, if you are using EF or scrap like that. So this is that, and then to write mass balance, you have to consider some inputs and some equations. These are essentially mass balance equations, except the last one. So you can write iron balance equation. Iron input is equal to iron equals in output. There is no mass generation or destruction. So it's overall iron has to be balanced in the process. Iron, silicon, carbon, manganese, phosphorus. All these equations, or the conceptually, it sounds very simple. However, once you start using plant data, you will find that very often those balances don't work out, and there is a significant error. That's why there is this large